Hello, everyone. I'm Owen Wilborn.
I'm Dolores Rodriguez.
I'm Joshua Basil.
And I'm Caitlin Wu, and we are tutorial group 5. So our topic is steady state heat transfer thermal resistance circuits model. And the resistance circuits model is important because it can be used to simplify complex steady state systems to analyze heat transfer within the system. If a system has heat transfer via conduction, convection, and radiation, the thermal resistance model allows for a simple problem setup. So one application of thermal resistance models for steady state heat transfer is in analyzing heat loss from a tank or pipe. So in this example, imagine you're designing an electric heater that has some kind of insulation, and you want to determine the ideal conditions under which heat loss is minimized. So you can use the thermal resistance model to determine the heater dimensions and insulation thickness needed to minimize the cost of heat loss. Then in the semiconductor industry, the model can be used to determine the conditions needed for sufficient cooling of board-mounted chips. So using the model, you can see how changing different parameters influences the heat flux and use that information to optimize cooling. And another application is in solar cell design. So as we saw in lecture, we can use this model to study heat transfer through solar cells and optimize solar cell efficiency by changing different parameters. And our last application of this model actually relates to the human body. So we can use the thermal resistance circuits model to model the steady state heat transfer through fatty tissue in varying convection conditions. So like calm or windy day, for example. And we can see like the corresponding thermal resistance circuit. It's shown in the slide as well. And then this is kind of just a summary of our motivations for using this model. But as you can see, the thermal resistance circuits model can be used for a wide variety of heat transfer applications. And we will see one way to apply it in our example problem later in the video. So here is just a topic overview. Some key takeaways. We're using equations from electrical resistance circuits and applying them to analyze heat transfer in steady state systems. And then another key thing to know is, series versus parallel resistance. So conduction through multiple layers would be series, and convection and radiation at an interface would be parallel resistance. And then we can also add parallel or series circuits together to simplify the circuit model and solve a large problem. We'll see that in our example problem as well. And using the circuit model for radiation is challenging because the terms depend on temperature. So if this is the case, then we'll get a non-linear equation, and we're going to end up needing to use like GOLSEEK on Excel or any other solver to solve the problem. And then on the right here, you can see some key equations that we're going to be using for this approach. So there's the resistances for conduction, convection, and radiation. And then the heat transfer coefficient for radiation is shown as well. And then in this table below, you can just see like the analogy between electrical and circuits and the thermal resistance circuit. And so you can see like for V equals IR, that corresponds to delta T equals Q thermal resistance. And then the series and parallel equations are shown as well. And then here is just like a list for general strategies for using this approach. So first, you'd want to identify the types of heat transfer occurring within the system. Then you want to draw out the thermal resistance circuit, paying attention to where the series and parallel resistances should be placed. Then you can write out the equations for your resistances and combine resistances wherever possible to simplify, a larger problem into a simpler one. And then you can write out the heat flux equation for your control volume and then plug in the resistance equations that you just wrote out. Then you can solve for your unknown. And then one key thing to know is if you have multiple unknowns, then you might need to write out like more heat flux equations for different control volumes to continue solving depending on the number of unknowns that you have in the problem. So if, like, for example, if you've already considered heat flux between T1 and T2, then you can consider heat flux between TH and T1 or T2 and TC. to isolate unknowns one at a time. And we'll also see this in our example problem later on in the video.
All right, so some things we need to cover before starting the problem is just some pitfalls that we could fall into. So one might be using the wrong circuit equation. So if we used parallel instead of series, using the wrong temperatures for radiation. So if we accidentally switched, if we used the wrong T1 and T2 to find the H term for radiation, then we're going to screw up our problem. And we may need to use GOLSEEK to find radiation resistance when both temperatures aren't known. Also defining the part of the circuit we're currently solving. So we can obviously mess up terms. We need to use the right T1 or T2 for a specific part. And we must use the correct resistance as well. And an alternative approach would be using the fundamental heat equations instead of the resistance model, since that's where it's derived from, but that would also make the problem more complex. And we could also find the heat flux through each media individually. So in this problem, we can see we're comparing two temperatures of air, TH and TC, which are known, we know the temperatures on the walls, and we're trying to solve for TH and TC, and that's going to be through convection and radiation, which are both parallel and parallel and series circuits. So this problem relates to the resistance model because it has parallel and series, right? It has convection and it has radiation. And the series circuit is going to be conduction, and then the conduction will be through the wall and total heat transfer from hot air through the wall to cold air. And this is applicable in any system where heat transfer is 1D. Composite walls are applicable in chemical reactors, which is what these are. So then first thing we need to do is define our variables. So we're using a copper bronze alloy. So then L1 is 0.1 meters, K1 is 26 watts per meters times Kelvin. We have our steel wrought carbon, which also has its variables. We have T1, T2, we're given H of the hot air, H of the cold air, and then we're given numbers for copper, bronze, and for steel. And so we want our temperature of our hot air, temperature of our cold air, and the heat flux. So then we can see in this diagram, we have radiation into our metal, conduction through the metals, and then radiation out. And we can also see that the slope in material 1 is greater than the slope in material 2, because material 1 has a smaller thermal conduction constant, and both have the same length. So some assumptions we have to make is that the air and walls in the hot and cold regions are very large compared to the composite wall. Therefore, our E surrounding is 1. It is also steady state because the T hot and T cold aren't changing, and assume the system has existed for a long time. The heat is only flowing in the X direction, which is why it's 1D heat flow, because the wall is much taller than it is wide. Convection and radiation occur between the air and the wall because the air is a fluid. And then the radiation emissivity equals the radiation absorptivity for the steel and copper by Kirchhoff's law.
All right, everyone. So now we're just going to briefly go into the strategy to solve it and the steps. We're not going to go through all the calculations, but covered what you need to understand. So first off, with any circuit diagram, you want to start by drawing the circuit. So we have the T hot to the T1 portion first. This is the air and wall on the hot side interacting. There was convection and radiation. And because the TH and T1 are going to be the same for both of them, we will draw that in parallel. Next, we're going to look at the wall. That's from the T1 to T2. Here, it's conduction because it is through a solid. However, there are two different metals present, the steel and the copper bronze. And so therefore, because they are smushed together, what has to go through first the copper and then the steel, we know it's going to be a series circuit between T1 and T2. And then the final one is T2 to T cold. And this is exactly like the T hot side, where you have the convection and radiation between the same temperature. So it's parallel. And so right here, you can see the full circuit drawn out. And now we're going to briefly describe how you're going to simplify the model. So first, you can separate it into 3 mini circuits. You can do the TH to T1 mini one, the T1 to T2, and the T2 to T cold. So by making it mini problems, it makes it easier to solve each variable. So where do we start? We're going to start on the by writing out the resistance for each of the 3 mini models. So we have the conduction, which is going to be the L1 divided by Ka for each of the terms in the middle. And then in the parallel one, instead of using the summation of R, we use a summation of 1 over R and then take the inverse of that. And so you see here for the parallel, we have 2 very similar equations. The only difference is there's going to be H hot and the radiation of the hot air on the hot equation, and using the cold in the cold equation. One thing to note is for radiation, you can write out the radiation term by using the sigma times the emissivity of the material, and then the squares of each temperature added up, plus the summation of the 2 temperatures, T1, Th, as you can see on the bottom. This is useful for resistance of radiation. However, it does make it difficult because you need to know both the surroundings temperature and the wall temperature to use it. So just very quickly, and then going into the do it section, we will start by looking at the conduction through the walls. This is because we know what T1 and T2 are given. Therefore, and also L1 and K1 are given. So we know the resistance of the 2 resistance in series. If we look back here, these 2 ones are the steel and the copper, and T1 and T2. So we can then solve for Q. And now what's also very important to note is that we can pretend that these parallel ones over here are like a series kind of in a combined problem. So then we know the Q from TH to T1, the Q from T1 to T2, and then the Q from T2 to TC has to be the same along each part because those are in series with each other. So once we find a Q through the wall, that has to be the same Q from the air to the wall in both the hot air and the cold air. So next we're going to look for the cold temperature. So by knowing what Q is, we can then write out the temperature drop based on TC, which we're solving, and we can write out the entire resistance of the parallel circuit on the bottom in terms of TC, the unknown. And so here's the example we have to use Gauss-Seek because the TC appears at the top of the equation and down low because it is also in the resistance term for radiation. And then, but it is a one equation with one unknown, so it is able to solve, and you get 283 Kelvin. Using the exact same approach, you can now do it for the hot side, where you again start with the difference between T1 the known and TH the unknown. You write out the equation for your resistance down here in terms of TH, also the unknown. You plug in the known variables. Again, Q is the same, it's 231, and then you can solve for the hot temperature. What's really nice about the resistance model is how you were able to see we separated into 3 mini problems and solved each like mini circuit individually. You can then check by making it the entire circuit. So if we go back to the entire circuit, it would be the convection radiation of the air to wall. Then it would be the conduction through the wall, then the convection and radiation of wall to air. And so we can create an equation that has all of these terms in it. As we see here, we have first parallel circuit, then we have the 2 circuits in series, then we have the next parallel circuit, and they're all added up because each 3 of the mini circuits were in series. And because we're looking at the entire thing, we now use TH and TC on the top for delta T. By using a TH, TC that we solved for and a T1 and T2 that were constant and given, we're able to solve for each resistance term. and then plugging it in, we can get the full resistance term at the bottom, and we already know what TH and TC are up here. So we can plug those in. And what we find is when we do that, we find that the QX is again 231, which is exactly what we calculated back in the first part for the QX through the wall. And so this can verify that we did the circuit problem correctly, because the QX through a series circuit is the same along any parts of the resistance because it is in series. So yeah, that's really nice being able to kind of do smaller parts and then bigger parts and jump back and forth. But now we're going to generalize.
All right, yeah. So just like Owen said, we're going to generalize the problem and kind of explain what happens when we change certain parameters. So if we change the wall material, so use different metals with higher or lower conductivities. If we choose a new material with a higher conductivity for either side, we'll end up having a larger heat flux, and then the temperature difference between T1 and T2 will increase, and the value that we calculate for TC and T8 or TC will end up decreasing and TH will increase. And then if we use a material with a lower K value, we'll end up with a lower heat flux, a lower temperature difference, and TC increases while TH decreases. And we also have, so we have a diagram of kind of representing our system, and then the equation so you can kind of mathematically see why they would increase or decrease. And then we have two different graphs. The one on the left represents K2 and the one on the right is K1, but they look very similar. They're just showing different ranges of values. But as you can see, as we increase the thermal conductivity, heat flux increases. And then as we decrease as we have higher heat fluxes, the temperature of the cold air decreases. But as we have higher heat, as heat flux increases, we'll have lower cold air temperatures and then higher hot air temperatures. And then moving on to if we were to alter the surface temperatures, so T1 and T2, if T1 increases and T2 stays the same or decreases, or if T2 stays the same or T2 decreases while T1 stays the same, heat flux will increase, so the calculated cold air temperature will decrease and the hot air temperature will increase. If T1 decreases and T2 stays the same, or T2 increases and T1 stays the same, heat flux will decrease, so the cold air temperature increases while the hot air temperature decreases. And if we were to change the material lengths, if L1 and or L2 increase, the heat flux will decrease and TC increases while TH decreases. If L1 and or L2 decreases, heat flux increases while TC decreases and TH increases. And then just to kind of generalize, so when you're changing the variables, kind of connect how it'll affect heat flux, because basically any variable that you change will end up changing heat flux. If K increases, the heat flux of the wall increases, therefore heat flux from air to the wall increases, and then the delta T of air to wall increases, and then TH increases and TC increases. So so all the parameters kind of affect the heat flux, and then heat flux affects everything else. And thank you for watching.
We will put a link to the YouTube video once we upload it here, and that will be in the PowerPoint at the end. But yeah, thanks. And then, oh yeah, some references, and that's all.